Good afternoon and welcome to Chapter 18, Thermodynamics. Thermodynamics is the study of heat and heat transport, or how it goes in between objects and substances. The most fundamental building blocks of thermodynamics are the conservation of energy, which we've already discussed at some length, and the fact that heat goes from hot to cold. Sort of common sense, but also incredibly important. When two objects are in contact and they have the same temperature, as we've talked about before, we say that they are in thermal equilibrium. That is, that they are not able to impart any kinetic energy one way or the other in between the substances. If two objects with different temperatures come into contact, they will try to get to thermal equilibrium. That is, the hotter object will try to impart some of its heat, its thermal energy, to the colder object. And I apologize, it looks like the box has gotten slightly out of alignment here. That's a little better. I think it's just drifting into later afternoon, so the sun is trying to come directly in the window through the blinds. In any case, if two objects come into contact, they will try to reach a state of thermal equilibrium. That is, that the hot object will try to impart some of its thermal or heat energy into the colder object, and the colder object will receive the heat or the thermal energy, the thermal kinetic energy from the hotter object, the object with the greater temperature. Until finally they have the same temperature and neither one of them are willing to part with any more heat or trying to accept any more heat from the other. As a matter of fact, we usually call this by a very fancy name, that is the zeroth law of thermodynamics. Now, I've included a graphic. It should be both in the course files and also on the Chapter 18 splash page. The zeroth law of thermodynamics basically states that if two systems are in thermal equilibrium with a third system, then they're also in thermal equilibrium with each other. This is the old algebra identity: if A equals B and A equals C, therefore B equals C. And in this case, of course, we're talking about the temperature of these three systems, A, B, and C. If we put heat into a system, it can change the system's temperature, but it can also increase the pressure of the system or increase its volume. And if you remember, we talked a little bit about this when we talked about the ideal gas law. This, of course, can happen even if you're not talking necessarily just about gases. We say heating the system is giving it internal energy. In theory, there is no upper limit to temperature. Increasing the internal energy increases both the pressure in the system and makes it expand its volume. Largely, of course, in the case of a gas, you can see the pressure and the temperature and volume change quite readily together. When there's no kinetic energy left in a substance, the substance takes up zero volume, has zero pressure, and stops existing. You guys remember what temperature this is called? That's right, absolute zero. That's, of course, at minus 273.15 degrees C, or at 0 Kelvin. For those of you who are wondering, it's something like negative 459.7 Fahrenheit. That nasty temperature scale that we are strictly verboten or forbidden from using in science because it's dumb. In contrast, the freezing point of water is 0 degrees C, or 273.15 Kelvin. The boiling point is 100 degrees C, or 373.15 Kelvin. And those are 32 and 212 F respectively. But like I said, we're not using Fahrenheit anymore. Now, a system can also use this internal energy to do work, like burning gas, pushing a piston in an internal combustion engine, something along those lines. As it does so, it takes energy out of the system. Thus, the first law of thermodynamics is different from the way that Morty stated it at the end of episode 1, season 1. And if you remember, sometime after he had the mega seized removed, when they were standing around in the garage, and Rick orders him to state the first law of thermodynamics, he stiffens up and says something along the lines of, the increment of heat supplied is equal to the increment of internal energy. But that's wrong. 20% right as usual, Morty. The way it actually goes is that the heat added to the system is equal to the internal energy by the system minus the work done by the system. Remember, work and energy have the same units, and if you imagine that you're going to burn some gas, for example, in the example of the internal combustion engine, obviously it's going to heat up, but also it's going to expand. Some of that energy is going to do work in pushing the piston. And so it's not all just going to go into the heat or the temperature or the internal energy of the gas. Now generally we write this two ways. We say Q minus W equals U. Sometimes. That is, heat, Q, minus the work done, W, is equal to U, the change in internal energy of the system. We can also equivalently say Q, or the heat in a system, or the change of heat in a system, is equal to W, the work done by the system, plus the U, or change in internal energy of the system. Long story short, if you supply heat to a system, it can either change the internal energy of a system, do work, or both. Heat is energy, energy can do work. Now, there are a lot of different kinds of processes by which things can happen thermodynamically. The first one we're going to look at is what we call an adiabatic process. Adiabatic processes are processes where the heat added to the system is zero. So this is like a process that happens inside a cooler or inside a thermos or something, where there's no heat being put in or taken out of the system, right? It's isolated and not taking any heat into the system from the environment or releasing any heat into the environment. Thus, the work done equals the change in internal energy. Or you could just say W equals U, something like that. Another way of saying that is that the system does work, it cools off. The classic example is if you blow into your hand. If you blow like this, open mouth, it feels warm because the air doesn't expand. But if you blow with your lips together, and you can feel the air the stream of the air much further away, as it's going through your lips, it goes through this tiny little opening, but by the time it gets to your hand, you can feel it all over. It has a chance to expand, and in so doing, it does work and takes internal energy out of the system, cooling the air off. And that's why if you put your lips together and blow, the air feels cold, but if you just, it feels warm. It is for this reason that in meteorology they say air temperature rises when heat is added or pressure increases. For adiabatic processes, like inside the thermos or what have you, this reduces to air temperature rises as pressure increases. This is equivalent to, you might have guessed it, hot air rises, right? Doing work against gravity. What does this mean? Where it should be warmer in the upper atmosphere, where should it, be warmer? In the upper atmosphere or here near sea level where the temperature is higher? As a matter of fact, the temperature of air decreases by 10 degrees C per every 1 kilometer that it rises. If a strong wind blows warm air up a mountain range, then as it gains altitude, it can cool, causing condensation and precipitation, or rain. Sometimes snow if it's really cold, obviously. But this, of course, is only if the air has a sufficient amount of water vapor in it. As the air comes down over the mountains, it can warm back up, causing a strong wind. Remember, temperature means kinetic energy. Have you ever noticed that it's always really, really warm on an airplane? Well, airplanes generally fly, 30,000 feet or something like that, several kilometers above the surface of the Earth. And if it's supposed to be 10 degrees C cooler per 1 kilometer above the Earth's surface, why is it so hot on an airplane? Well, that's because inside this pressurized cabin where we're all sitting, we have to have about 1 atmosphere of pressure. And since the cabin is pressurized, it can stay warm. The cabin warms the air. But that also means there has to be constant air conditioning to remove heat from the cabin, or else it would probably warm up to about 130 degrees C, and we would all cook and be very uncomfortable for the very short amount of time which we lived on the airplane, which honestly probably wouldn't be very long. Sometimes a layer of warmer air can get stacked up on top of some denser warm air. We call this temperature inversion. If this happens, smog and other pollutants can get caught in the thermal layer, spreading out at an altitude, fanning out at a certain height above the surface, instead of dispersing into the atmosphere. Because these adiabatic processes are not unique to the atmosphere, they can happen in the ocean, which is why El Niño is a recurring phenomenon. Heating of the sea floor happens because of convection currents in the magma below the surface of the Earth. Now, I've included an image of this temperature inversion both in the course files, and I've left a link to it in the Chapter 8 description. You should be able to find it there. Moving on, the second law of thermodynamics can be stated in several ways. Sometimes we say that there's no such thing as a perpetual motion machine. Sometimes we say that real processes are not reversible. But the standard textbook version of the definition of the second law of thermodynamics states that the entropy in a system, which is a measure of how disordered the system is, that entropy always increases when a system undergoes any real process. If you wanted to write that out in math terminology, you'd say ds, or change in entropy, is greater than dq, or change in heat, over T for a given temperature. And without getting into all of the calculus and math mumbo jumbo, that just really means that the entropy, or the measure of disorder in a system, always tends to increase, not to decrease. This is actually a really loaded statement, and it means quite a few things. The net positive change in entropy means that real processes, things that actually happen in this world, are not reversible. For example, let's say you go to the doctor and you get a flu shot. You can pull the syringe back after you've gotten your shot, but the medicine that got shot into you from the flu shot is not what's going to come back into the syringe, right? Most likely it's going to be maybe some of that, but mostly it's going to be your blood. Because real processes don't happen in reverse. That would be like putting 100 flies in a jar inside a huge warehouse and opening up the jar and expecting to come back at some later time and finding all 100 flies back in the jar. Or let's say 1,000 flies even, or a billion of the same particles in the same configuration. That doesn't happen in real life, right? This means that there is a specified or specific direction for the energy in thermodynamic processes. And that means we get to the punchline: heat goes from hot to cold. We can only add heat to an already warm system by doing work. And that's how your heater works. Notice that it costs you power, costs you energy. Yeah, if you don't run the heater, your electricity bill isn't as high, right? That's the work that the system does at the cost of electrical energy. The second law of thermodynamics also states that there is only so much efficiency that you can get out of a heater or an air conditioner or an internal combustion engine, whatever kind of heat engine you have in question. This version of the law of thermodynamics, the second law of thermodynamics, excuse me, states that there can be no perpetual motion machines because the entropy of a system always increases. And what that means, basically, is there is no such thing as a 100% efficient machine. At the very least, you're going to have some kind of interface with the environment, and so you're going to lose heat from friction or what have you. As a matter of fact, in 1824, long time ago, almost 200 years now, a French engineer named Carnot realized that the maximum amount of efficiency that a heat engine can have depends upon the temperatures that the heat engine runs in between. There's an efficiency equation, it's in the lecture notes. Efficiency is equal to T hot minus T cold, excuse me, the two temperature extremes that the heat engine runs in between, divided by T hot, or the heat reservoir, the driving heat that runs the heat engine. Now you have to be really careful if you're actually going to carry out one of these kinds of calculations, because if you don't use the right units, you will get a nonsensical result. For example, what if your T hot or your T cold is a negative number? Then you could end up with a negative efficiency. It just doesn't make any sense, right? And so the proper scale to use, the proper unit to use for an efficiency calculation, and indeed for just about all temperature calculations in thermodynamics, is obviously not degrees Fahrenheit, that's right out, but it's also not degrees C. You have to use absolute temperature or Kelvin. Okay, that's the only way to get it right. The typical application of this is this thing that we call the steam turbine. And I've also included an image of this one as well. Heat goes from the hot reservoir to the cold reservoir, pushing the blades of the turbine and generating electricity in the generator. We'll talk a little bit more about how that actually happens in Faraday's law in the upcoming weeks when we start to talk about electricity and magnetism, or electrodynamics. Now, as this steam turbine does work, the temperature drops along with the pressure and it condenses back into water. Remember, the heat supplied is equal to the change in internal energy and the work done. So as this water does work, it's going to cool off a bit. But can pressure really be reduced so spontaneously by condensation? Well, if you don't think so, I've also included a link to a video where a soda can crushes itself under atmospheric pressure. Essentially what happens is the atmospheric pressure outside the can is greater than the low pressure inside the can drops as a result of the little bit of water inside the can boiling. So when the water vapor comes into contact with the cold water and everything cools off, the pressure inside the can drops very sharply, and the the vapor pressure outside the can is still 1 atmosphere, and it crushes the can almost instantaneously. In any case, I hope you've enjoyed this video. I will see you all on Thursday for lab.